In this work, we utilize part-wise motion priors and learn human-object interactions for a physically simulated character. Our goal is to generate human motions of daily lives interacting with the environments around us. To do so, we need a model that can represent motion variability. The motion variability largely comes from the variations for the individual body parts. Among the body parts, hands are especially crucial for daily interactions. For example, imagine your body movement when you climb on a rope. You need to firmly grasp your hands to the rope and then move your body accordingly. We use physics-based approach to generate realistic human motions. The physically based methods have demonstrated success on imitating motion clips or generating sports scene. The major challenges here is that they heavily rely on the motion capture data, just like other data-driven approaches do. However, existing motion capture datasets cannot extensively cover the range of real-world motions. For example, if you see the statistics of Lafan 1, which is one of the popular motion dataset, the data distribution is biased to certain types of motions. Also, it is not easy to concurrently capture the interacting hands and body with the paired objects due to the occlusion or intricate movement of hands. To overcome these issues, we propose a method to enrich the possible motion variations by combining part-wise motion obtained from various sources. Importantly, our agent features realistic hands that actively interact with the environment in diverse scenarios. We also suggest a training technique to stably combine imbalanced part-wise motion data into a coherent whole-body motion. Our method leverages the adversarial motion prior, which trains an agent to imitate reference motions. Policy here is trained to maximize cumulative reward, and the reward for each time step is calculated from the weighted sum of task and style reward. Task reward is manually designed according to the task goal. To reduce effort to invent a reward term for naturalness, AMP trains the discriminator and it gives reward when the agent exhibits similar motion to the dataset. The discriminator is trained to predict whether the observation comes from the motion captures or the online trajectories of the agent. Instead of a single discriminator, PMP assigns dedicated discriminators for different body segments. Given the multiple part-wise motion priors, our total style reward is the product of the individual style reward RKS. By using multiplication instead of summation, our formulation ensures that all of the body segments closely adhere to their respective reference motion. We find that this simple modification not only combines part-wise motions but also effectively balances all the separate motions as well. We attribute this to the physics simulator. The simulation only allows physically valid whole-body motion and filters out combinations that result in awkward postures. We showcase brief example where agent finds best combinations of the part-wise motions. In this scenario, we divide body segments into two parts and then use locomotion data and looking around motions for the limbs and trunk respectively. Finally, an agent is trained to navigate to the body goal while keep track on the gaze target. As you can see, agent maintains the natural motions combined from the different data. However, we need additional device to stabilize training. When we mix the different parts with product of the rewards, the value can vanish if only one of the reward is small. We define it as reward vanishing problem, and it can cause failure of training, especially when the number of parts increases. To relieve this issue, we suggest demo blending technique. In addition to the training trajectories from the policy pi theta, we randomly mix sample trajectories from dataset MK for kth body part. The demonstrated trajectories from the dataset guarantee the high style reward, which allows agent to capture valid signal in the early stage of training. Since it is hard to capture hand-object interaction precisely, hand needs additional motion priors. Therefore, we suggest a method to substitute motion capture for the hand and objects. We extract reusable interaction prior from the another hand-only simulation and use this as an interaction prior for the hands. The major benefits for the simulated trajectories is that we can fully provide guidance to our agent with the physical states and the actuated torques during hand interaction. Also, you can use any types of existing hand models that can exhibit dexterous skills. In summary, the total style reward is the product of all the part-wise motion priors. For hand parts, which is denoted as H here, we dynamically mix the style reward Rs and the interaction reward Ri. Sigma dynamically balances the ratio of the mixture based on the distance to the interaction target. Please refer to the paper for more details in the equation. We first demonstrate the capability of the proposed method to effectively assemble part-wise kinematic priors. In this scenario, the agent is trained to carry a ball walking up the stairs to reach the goal. We use walking motion in both plain ground and the stairs as the reference for lower body, while using carrying idle motion as the reference for upper body. Our framework allows agent to successfully combine each part-wise motions as shown here. Note that the red stair represents the goal and the blue points are the height map. For comparison, we train an agent with a single discriminator with fully coordinated motion data. Though the baseline uses same amount of motion, it generates awkward motion since it cannot combine the motion captures. Additionally, we present the motion augmentation task. In this experiment, we divide the body into 7 parts and create an additional group for shoulders and hips to represent limb coordination. This allows us to augment normal walking motion to the various styles such as soldier and hopping style. Among the augmented reference, the hopping style motion is physically implausible. However, by using our agent with the demo blending technique, our agent successfully imitates the style of the correct reference. Next, we showcase the effectiveness of proposed interaction prior with the scenarios where hand is crucial. In the cart pulling scenario, we verified that pre-trained interaction prior is reused and also generalized to the various types of grasping styles as shown in this figure. With the reusable interaction prior for grasping, our agent can exhibit successful control on the several challenging tasks such as lifting a heavy barbell, hanging and moving on a bar, or climbing on a rope. You can check additional experiments and comparisons in our online video. In conclusion, we present a framework to incorporate part-wise motion priors and generate diverse realistic interactions that does not exist in the database. Our method facilitates reusable interaction prior extracted from hand simulation and enables dexterous skills. Additionally, we stabilize training with demo blending technique, which effectively finds a plausible combination that satisfies multiple part-wise motion priors. However, the proposed methods still require considerable effort on designing an appropriate task-specific reward. Also, the body segments are manually selected by the user, so the future direction may automate this process. Lastly, the policy in our framework eventually converges to the certain mode of assemble skill at the end of the training. Our future direction may allow agent to dynamically change the styles of assembly after the training. Thanks for the listening.